So, hello everyone. Today we will be discussing the lab assignment 2 solutions of numerical analysis and design. My name is Siddharth Gupta and my roll number is IT222482. My enrollment number is 3240206. The first question is for writing the code for finding the roots of polynomial equations. We need to write the Python, C or MATLAB code for finding the roots using bisection method. For again, the assumptions that we require that a function must be continuous and fa into fb must be negative for the root's existence. And the geometrical interpretation we already know that it will repeatedly cut the x-axis into half. Now, starting with the Python code for bisection method, first we will creating a function where we have passed f a function a, b, and tolerance. If fa into fb is greater than equal to 0, we will return none. Then we will start a loop till b minus a by 2 is greater than tolerance. Till b minus a by 2 is greater than tolerance, we will continue this loop. The loop says that we will initialize mid with a plus b by 2. If f of mid, function at mid is greater than equals, is exactly equals to 0, we will break the statement. Elif, we will check fa into f of mid less than equals 0. Till fa into f of mid is less than 0, we will put b is equal to mid, else we will put a is equal to mid, and we will return a plus b, that we will return the mid value. So till the while loop b minus a by 2 is greater than tolerance limit, we will do this. And till f into fb, if it is less than 0, we will put b is equal to mid, else we will put a is equal to. And we will continue this loop. As it becomes less than 0, we will return the mid as the root. So it is the time complexity for bisection method will be log of b minus a by tolerance, and space complexity will be big O of 1. So this is the code for bisection method. Moving on to the code for Regula-Falsi method. For Regula-Falsi method, the same assumptions that the function must be continuous and fa into fb must be negative for root existence between a to b. The the geometrical interpretation will be a straight line or secant. You can say that will be passing from a comma f and b comma fb. The Python code for Regula-Falsi method is we will create a function again same thing f a b tolerance, and maximum iteration will say it will be 100. Again, we will check the same thing that if f into fb is greater than 0, that is the roots will not exist. So we will return none. Hello, we will return none. Then we will start a for loop from I in range till max iteration, and we will say p is equal to, like again that mid thing, that is m is equal to a into fb minus b into fa upon fb minus fa. Till this absolute value of f of c is less than tolerance, we will return c. If f into fb is less than 0, we will put b is equal to 3, else we will put a is equal to 3, and we will return c when we come out of this loop. So this is a simple Python code for Regula-Falsi interpretation. The time complexity will be log of 1 by tolerance, and space complexity will be big O of 1. Now coming for the Python code for finding the roots using secant method. Assumptions required that the function must be continuous, and there will take two guesses x0, x1, and they do not need the to bracket the root. The geometrical interpretation, similarly, it will be a straight line, or you can say a secant or a chord that will pass from a comma fa and b comma f. The Python code for secant method is we will pass on a function x0, x1 tolerance and max iteration. Again, same thing for I in range till max iteration. We will, if f of absolute of fx minus f of 0 is exactly equal to 0, we will return none. Else x2 will be equal to x1 minus f of x1 into x1 minus x0 upon f of x1 minus f of x0. This is the formula for secant method. And again, we will check if absolute of x2 minus x1 is less than tolerance. We will return x2, and x0 comma x1 will be equal to x1 comma x2, and we will return x1. So this is a simple implementation Python code for secant method. Moving on to the algorithm time complexity of secant method. So it is convergence is superlinear, and the order of convergence is 1.612, and time space complexity is big O of 1. Now moving on to the 1.4, writing the Python, C or MATLAB code for finding the roots using Newton's method, or you can say Newton-Raphson method. Again, we will assume that fx is continuous and differentiable, f dash x is not equal to 0, And initial guess we will take x is equal to 0, that must be relatively closer to the actual root. Like we will take a point B that is actually closer than A. Now the geometrical interpretation for Newton-Raphson is a tangent that passes through the x0, and the x-intercept of this tangent becomes the next approximation x1. Now moving on to the code for Newton-Raphson. So we will pass on the function with f, that df is the differentiation of the function, x0 is the starting limit, tolerance is that 0001, max iteration is 100. Again, we started with a for loop from 0 to, you can say, max iteration, like till 100 it will go. First, if differentiation of x0 is 0, we will return none, as we already assumed that it should not be equal to 0. X1, now the formula for Newton-Raphson, that x1 is equal to x0 minus f of the x0 upon df of x0. If absolute of x1 minus x0 is less than tolerance, we will return x1, and again we will initialize x0 is equal to x1, and this loop will go on until this becomes greater than tolerance. And as it becomes greater than tolerance, the previous value of x0 will be the root. So this is a simple Python code implementation for Newton-Raphson. The quadratic convergence, it will be having a quadratic convergence, and the time complexity will be big O of log of 1 by tolerance, and space complexity will be big O of 1. Moving forward, for the Python C MATLAB code for finding roots using fixed point iteration. For fixed point iteration, the assumptions required are assuming that the functions can be written in the form of x is equal to gx, and g dash of x mod is less than 1 near the root to ensure convergence. Geometrical interpretation finds the intersection of curve and the line. The sequence form a staircase pattern converging into the intersection point. Now, the Python code for it is, we will pass g, x0, tolerance, max iteration is equal to 100. We will start a for loop, and we will firstly write x1 in the form of g, x form. And if absolute of x1 minus x2, again that part, if it is less than tolerance, we will return x1, and we will put x0 is equal to x1, and the root will be x0. So we will return the root. So this is simple, like for loop will run till here. Another for loop, it will check the tolerance. As tolerance will return less than 0, it will return x1, and we will again initialize x1 to x0. So this is a simple Python code for fixed point iteration. The convergence will be linear, and the time complexity will be dependent on the formulation of gx, and the space complexity is big O of 1. Now moving on to the second question, for writing Python C MATLAB code for interpolation. Starting with Lagrange interpolation, we will assume that the data points are not equally spaced, and these are already given to us. Now, geometrical interpolation will be a polynomial of degree n passing through all n plus 1 given data points by creating a linear combination of basic polynomials. Now, Lagrange interpolation Python code, we will take the inputs x values and y values that a user will give, and x is the interpolated value. N is equal to len of x values, n is the number of data points that we will find by using length function. Result we have initialized with 0. We started a for loop, and we have initialized term is equal to y of that, the y part, y array, I, and for j, another for loop for j in range of n. If I not equal to j, this is the formula for Lagrange. Term will be equal to term is equal to x minus x of vals j upon x vals of I minus x vals of j, and the result will be added back to the term, and we will return the result. So this is a simple Python implementation code for Lagrange interpolation. The time complexity will be O of n square, as you can see two for loops coming here nestedly, and the space complexity will be O of n to store the data. Moving on to the Python code for Newton interpolation forward difference. So again, we will assume that the data points must be equally spaced, and the forward difference table is already computed. Now, moving on to the code. So the Python code will be, we will start with a function where we have already passed on the x values, y values, and the interpolated value, and will be a random number of data points using len of x values. We will find the difference that will be equals to O into 0 into n for I in range of n. For I in range n, we will put the difference of I0 is equal to y of s, else for j in range, and for I in range, we will construct a forward difference table. After constructing the forward difference table, we will find the value of h and u using these formulas. We will take our resultant, take u term and initialize it with difference of 0, 0, 0 and 1. Now, for I in range 1 to n, we started the for loop. U of term will be equals to u minus I minus 1 by I. Like this is that u minus 1, u minus 2, u minus 3 by 1 factorial, 2 factorial, 3 factorial. This is that part. And we will add it to the resultant. That resultant will be equal to u of term into difference of 0 comma I, and we will return the result. So this is a simple Python code for Newton forward difference interpolation. The time complexity for difference table will be big O of n square, and the time complexity for evaluation is big O of n. The space complexity is big O of n square. Now moving on to the numerical quadrature formulas. Now we will be proving the Python CMATLAB code for numerical quadrature using Newton codes formula. So the assumptions we will require that the integrals fx can be approximated by piecewise polynomials. Like we can break the integrals in many parts, and points must be equally spaced. As we already know for Newton codes formula, points must be equally spaced. It is the fourth question of our part of our lab assignment solution. Second, the geometrical interpretation will be. Yes, like you can say, like it will be a curve that will be broken into many trapezoidals or many parabolas, and we are adding all this to find the final integration. Now moving on to the implementation Python code for trapezoidal and Simpson's 1/3. For trapezoidal rule, again the same thing. We will find the value of h, and we will already put fa plus fb, that is y0 plus yn, the first and the last values in the resultant. We will start a for loop and we will say resultant is equals to resultant plus 2 into f of a plus ih, and we will return h by 2 into resultant. So this is the final Python code for trapezoidal rule. Now moving on to Simpson 1/3, it is pretty the same thing, pretty similar. It is like we will finding the value of h as we did, again finding the resultant as we did in trapezoidal, again starting the same for loop, and here the only thing is we will put a ternary condition here that if factor is equal to 4, if I mod 2 is not equals to 0, else resultant is equal to factor into f of a plus I s, and we will return h by 3 into resultant. So this is the simple Python implementation code for Simpson's 1/3. Now moving on to time complexity. Time complexity will be big O of n, and space complexity will be big O of 1. Now moving on to linear equations. Linear equations, that is simultaneous equations, where we will be, this is the fifth question. This is the fifth question. Moving on to the fifth question. In this, we have to write the Python C MATLAB code for Gauss elimination method. First, we will assume that the system is AX is equal to B form, matrix is non-singular, that is determinant of A is not equal to 0, and leading principal minors are not 0. The geometrical interpolation, as you already know, there will be two lines, so they will intersect. It will form a upper triangular equivalent, enabling extraction of intersection via back substitution. Now, the Python code for Gauss elimination will be, we will be passing two matrices A and B. N will be the length of the matrix. We will start for loop. For this is the part for creating a upper triangular, or we can say triangularization, and this is the part for substitution. Now for triangularization, we will start a for loop from k to n minus 1, another I loop from k plus 1 to n. We will find that factor is equal to a of ik upon a of kk. For j, another for loop from j is equal to k to n. We'll say that aij will be equals to aij minus factor into akj, and bi will be equals to bi minus factor into b. Now from here we have already converted our augmented matrix into upper triangular matrix. Now similar, what we will do, we will perform substitution, back substitution, where for I in range n minus 1 minus 1 minus 1, s is equal to b of I. We will start a for loop from j till I plus 1 to n, and s will be equal to s minus aij into xj, and again we will print x by here. By finding here, we will print the value of x1, x2, x3. That will be the roots of the equation. So for forward elimination, or you can say for triangularization part, the time complexity will be big O of n cube, and for back substitution is big O of n. So you can clearly see from the loop part. The space complexity will be big O of n square. For matrix storage, you will store the matrix here. So big O space complexity will be big O of n square. Now moving on for Gauss-Seidel method, like writing the code for Gauss-Seidel method. Again, the same assumption that matrix is diagonally dominant and the system has a unique solution. Geometrical interpretation will be iteratively, it will move along the coordinates axis, and by using the most recently updated values immediately, it converges faster than Jacobi. Now, the Python code for Gauss-Seidel method is, first we will pass A, B, tolerance and maximum addition is equal to x. N is equal to length of b. We have find the length of b and we have stored it in n. X is equal to 0.0 into n. Now we will start a for loop from 1 to maximum iteration, and we will say x old is equal to x dot copy. Now for I in range, s is equal to b of I. For j in range, if I is not equal to j, we will perform this formula for Gauss-Seidel. ये रुक जा रहे